The sharing for the meeting.
Okay.
Well, you can allow me to share now. Let's see. I'm going to give you. Can you all hear me properly? Okay. Jerry, can you hear me? Right?
Yes.
Okay. Yeah. I'm going to give you a broader definition of resonance. So what Siobhan was talking about initially for the first 9 slides was the classical definition of resonance, right? Which is we have a system with like a mass, damper, and stiffness, or inductance, capacitance, resistance, and that then it's a second order system that has a natural frequencies, and if the external uh, excitation has a frequency that is matching to this, then you have a resonance. That's the classical definition of resonance, right? But that applies to primarily a closed system which does not exchange matter or information with the outside, and it only receives some kind of external forcing energy input. Whereas what Siobhan was calling as a dissipative system, which I call as an open system, it exchanges mass and information across its boundary. This is a big difference. During its interaction, it is exchanging mass and information. And that's systems which have a very different type of behavior. That's what I want to talk about. And before I go there, I'll also present. I'll also present a slide to say only conductance in an LRC circuit is intrinsic. The inductors and capacitors are manufactured. That is the rate of change of conductance. If it is fast increasing, that becomes an inductor. If it is decreasing, that becomes a capacitor. So it's a second order system can be viewed as a first order system with a variable conductance or a variable mobility, which is the inverse of the damping. And such system, when they are open systems, they behave differently, and that's what I'm calling as adaptive resonance. Okay, and also another thing I would like to point out is just because we take data and we observe power in a certain frequency, it doesn't mean that the underlying system is in an oscillatory mode. That is, what is important is to understand what is the event interval distribution. That is, what are the excitations that are happening. And for any given excitation, for an impulse, what is the response of the system, the response pulse shape? Together, these two things produce all kinds of spectral powers. And just because you observe a response in a frequency, it doesn't mean that it's a natural frequency system. I'll show that with a paper representation. So after this kind of non-disclaimer, I'll just jump into this concept of adaptive resonance, which I have actually talked to you all quite a bit before. Basically, a system that has some internal components, a large number of components that can be parameterized and can be viewed as a continuous system. When it sees the input from the outside, which are discrete, like a Poisson type of input, then you end up with an emergent mechanism when the two are adapting to each other, and you get a aha moment or an emergent reaction, and that becomes a Markov chain. And the key point here is this is a single step process. We are not talking in that case about a lot of oscillations, a long-term phenomenon, kind of discrete step jumps. Now, if I don't know whether that is an accepted definition of adaptive resonance, but
Ram, is this a broader definition or is this a narrower definition?
No, I think of it as a narrow definition is that you have to have a second order system and where the frequencies match. I'm saying that this is more like a cognitive resonance, or what Siobhan called as the social resonance. I'm kind of starting from his slide 10. The previous 9 that he had were like a mechanical systems, right?
I understand. Yeah. I'm only questioning the title of the slide.
Yes.
Broader or narrower?
I feel it is broader because anytime something works with another, and the result, two parts working together to create a whole. And the whole could be very different from the sum of the parts, right? And when that kind of a phenomenon happens, could we call it a resonance? If we do call it a resonance, then I'm thinking it's a broader definition. Now, what do you think, Jerry?
I have no
Well,
further
it's a
thoughts about it.
different one. It's a different definition.
Yeah,
But
yeah, it's an well, actually,
Yeah.
what I want to refer here is there is a book, the work done by Professor Stephen Grossberg. He is from Boston University. He has been working on this for the last 50 years and published tremendously. His work is called Adaptive Resonance Theory, or ART, A-R-T. Okay, he used to be at MIT, then moved to BU and started the Brain and Cognitive Science department there. And his book is called The Conscious Mind and Resonant Brain.
Thank you.
You
Yeah.
can't. Okay, so he coined the term adaptive resonance theory, and it is all about this kind of activity where there's something inside the neuron is continuously changing its state. For example, it is receiving some neuromodulators and it is releasing proteins which become the receptors that go on to the membrane of the neuron. Then the receptors change the conductance, right? So if there is a sudden release of large number of conductance, that you can think of it as inductance. But if there are no release of receptors, and the receptors have a half-life period, when they start closing down, it becomes like a capacitor. So you can really think of the membrane as a LC inductor capacitor system. And then, of course, the conductance is the inverse of the resistance. So it's an LRC. You can think of it like a second order system, but it is induced by rate of change of conductance. Okay. And then from the outside, you have synapses and all the dendrites and the spines and the synapses that are bringing in input into this. And they can bring in both neurotransmitters and the electrolytes. And the neurotransmitters then open up these receptors. So that kind of system, it is really not by definition, it's not a second order system. It's not a normal resonance. But however, it behaves like a second order system when suddenly things open up. Now, I'm talking about the neuron level or the cell level, but you can expand that to the mesoscale to the human being, between the body and the mind. And then you can take collective number of individuals and you can expand it to the society level. And so what I'm getting at is this concept of adaptive resonance, that is something from inside agrees with the something that is happening from the outside, which is what I think you called as the social resonance, is what I'm talking. But I don't want to restrict it to just society level. I'm saying that is intrinsic to all natural phenomena that we are seeing. Any kind of an open system is capable of exhibiting this, what we call as the adaptive resonance.
Can this be?
Rem, Ego has a question.
Yeah, sorry for disturbing you.
No problem. Stop me, please. Yeah.
Can this be related to the definition of what is intelligence? So basically, if you have a system which has the capacity to adapt its resonance, can this be related to the definition of intelligence, or maybe living intelligence? I don't know. Have they tried that?
Yeah. Yes. That is this line here. So what I'm saying is self-organization, which is what we have been talking about, a cybernetic process, which is reciprocal control and communication, is the cybernetics. And I'm saying that leads to self when there is a mechanism in the system to create this reciprocal control and communication, it becomes capable of self-organization, and the self-organization is the adaptive resonance. Ego, does it make sense?
Yeah.
Or no?
But it totally makes sense. This is why I'm asking.
Right.
There are several definitions of what is intelligence.
Right.
Right.
Intelligence is the ability of, let us say, a living system or some system for it to both live in the now and to create a memory from its experience to be able to adapt to the future events. That's the broad definition of intelligence. And that's why we have three things, right? We have the intelligence or the process knowledge, and then the structure and the function. So the structure and function keep morphing between each other, guided by this intelligence, and the intelligence consists of data structure, database, and query language, or you can call it learning, memory, and recall. And that becomes the brain of the system. Okay. So this is really what I'm going to be talking about. And then finally, I'm going to conclude that the punchline is this adaptive resonance. It can be good, bad, or ugly, exactly like what Suwon was saying, right? If this resonance between inside and outside happens in a constructive fashion, oh, that's great. The society changes towards something good. But if it gets dictatorial input and then you get biased information, the system goes kaput, then it gets ugly and it can have in between. So it can be good, bad, or ugly. We can't a priori know that it is constantly evolving. Okay, so this is the gist of my presentation. Oh, I forgot to turn on my timer. Okay, I'll walk through my slides quickly, okay? You've seen this before. I'm defining an open system as a system that consists of two parts: a system that is constantly changing within itself, and then there is external input that is coming. This external input typically is a discrete thing, and the interaction between these two is what we are interested. And in an open system, it leads to constantly this system changing from one metastable state to another state like that. But typically, it happens as an avalanche at threshold criticality, and it moves on to the next metastable state. So interaction between continuum and discrete. And in the past, I explained that I modeled this as a mixed random variable process, discrete and a continuous, and a Markov process, meaning one step at a time. And it is defined by time and population as opposed to time and space. Jerry and I had a big discussion on this. Space is nothing. I really would like to think of it as matter. This is where I have slight difference with Suwon saying that energy is the fundamental thing. I think of matter as the fundamental thing because energy is a derived quantity. It is human deduced, whereas matter is something we don't know how it came about its singularity, but matter exists. So starting with matter and the change in matter's position is what we are calling as time intervals, observation intervals. Go ahead. Igor, you have a question?
Continue.
You are muted. Igor, you are muted.
Yes,
okay.
I am sorry.
Yeah, okay.
No, I just don't totally agree, but let's go there.
Okay. Okay.
Yeah.
So in the first slide, I was talking about the discrete process, which is this thing that is influencing the system here, all the interaction that is coming from the environment. It can be modeled as pulses distributed at constant or variable rates. That's very important. It doesn't have to be periodic and have certain frequencies. It can have all kinds of rates. Okay, it can have random distributions, can have sporadic bursts. And also the pulse itself could have a pulse shape. And then the continuous system, it doesn't have to be an LRC second order system, could just be a first order system, exponentially decaying. It could even be critically damped. So if you look at the interaction between these processes, it leads to a memoryless process. I won't go through all of this. Basically, what I would say that the event occurrence is independent of past history, and that is why it's a Markov chain, and it happens at a critical threshold, and each change is a branch point. Typically, the system has to decide between exploration, which is going to new state, or exploitation, which is continuing to use the existing resources. So every change is a branch point. And key thing is that it's based on attractive dynamics and winner takes all. And I won't go through this. Each node in the brain, therefore, is a communication and control center. and it is in a metastable state. And when I say brain, it is kind of very generic. Any kind of interface between the system and the environment which does this translation, I'm calling it as brain. Okay, not necessarily human brain. I'm sorry, Subun, I don't know whether you're able to follow me. I'm not speaking fast. Okay. For one of the things I talked about before was that I was saying that the second order systems are really, sometimes it can be deduced quantities. For example, if you're looking at a plot of voltage versus current, if it has a nonlinear function here, then this nonlinear function, what it implies is the resistance is changing as a function of time. If the resistance or conductance that you want to look at it, if you think of it as the resistance, if it is increasing, it is a capacitive type of activity. If it is, if the resistance is decreasing, it is an inductive type of activity. So this curve can be modeled as an LR circuit or an RC circuit. And that is why in the neuron or any cell, when the membrane opens up, then the conductivity changes. Now, you can take that same analogy to a society, Jason. That is, if you open up the boundary of a nation, then you are changing the basic conductance and you are letting a lot of input in. And if you open it up too fast, then the conductance becomes inductance, and you're going to have a very large acceleration of charges coming in, or the outsiders coming in, and that can cause instability. Or conversely, if you completely shut it down, it is then the conductance, when it goes down or the borders are closed, it becomes a capacitor. And if you shut it down completely, it becomes an insulator. At that point, the system inside would just suffocate and die. It needs resources from the outside, and it needs some kind of interaction with the outside. But at the same time, you don't want it to be too porous. And that, so point I'm trying to make is, from the neuron level, you can take it all the way up to the individual level or to a society level, and you can see that the same idea of a second order system arising out of a nonlinear conductance, a first order system, is the cause of the resonances. So you can think of it as a frequency and a resonance. If the L and R are changing, the inductance and capacitance are changing constantly, okay, or if it is only one of them is happening, it's a first order system. Then, so the first point is, I talked about the system being first order versus second order. The other thing is, when I was showing the external input coming in, I was saying that the external inputs can be thought of as events. So the system is being event driven, and the events doesn't have to be fixed period frequency. And the events could be happening at all kinds of intervals. The most common thing that we can think of is the Poisson process. In the Poisson process, with a certain, in this case, this is a 40 hertz or a 25 millisecond Poisson process. But I should say this is work done by Perrenoud and Cardin in Yale University. I had invited them to come to our MIT seminar and present this. It was very, very nice work. I'm only showing one slide from their work here. If you're interested, you can read this. I'll share the slides. What they showed was, depending on how the interval between the events changes, you could get all kinds of response from the system here. No, if the events is changing, the input itself could contain all kinds of spectral power here. So a Poisson process, the beautiful thing about it is it has uniform energy in all frequencies. Okay, and then if it becomes sub-Poisson, that is, it is a narrower distribution than this, then it becomes has some spectral peak. And if it has become totally periodic, we're only talking about a point process here, a delta function being applied around this area. And if that's what happens, then it'll have energy in its fundamental and all its harmonics. And then there is something called super Poissonian process where it could have lots of different bursts. They could have a lot of high energy pulses that high frequency pulses coming in. But if you look at its distribution, predominantly it is also low frequency input here. So the point is, what is happening from the outside is not a fixed frequency, and it is going to be varying. That is, in the world, when you look at a society, all the time there is something happening somewhere at different types of intervals. Like you're in your local community, maybe every year the selectman is getting changed, and the House of Representatives are changing every 2 years, and the president is changing every 4 years. The senators are changing every 6 years. So if you look at a political system here, there are all kinds of events that are happening. But every time an event happens, that produces a lot of responses. And so the total response of the system is the sum of all these things. There is no one particular frequency that is driving. So the concept of resonance triggered by frequency, I want to change that. I'm trying to say that this is really an interaction that we are talking about, and the interaction could happen at different intervals, and it may appear like you have a pure tone here, but it is not. Okay. The reason I'm dwelling on this is a debate I'm having with all my neuroscience friends. They measure these frequencies now, which like what Sue was talking about earlier, the alpha, beta, theta, delta, and they think of it as simple harmonic things or sine waves, and they talk about phase clock and all those things. I don't believe those. 1 second, Jerry. Instead, that is not what is happening inside the brain, and because it is bombarded with lots of different inputs at many different intervals. Jerry?
Yes. So, yes, this is perfectly clear what you're describing, at least to me.
Okay. Thank you.
So I think there's strong biological evidence to support this.
Right.
But what is not clear to me is the origins of the initial diagram, which shows the instability of these different conditions and how this relates to the initial conditions. Now, I agree with this, the data presented here, as it is representative of natural phenomena, neural transmissions in the brain. Okay.
Yes.
But this is, and there is this huge variety of possibilities that because each neuron is in a separate, distinct location in the brain.
Right.
And that, so the question then becomes, how is this separate and distinct location of each neuron in the brain related to the initial conditions? I mean, and so without defining the initial conditions, this becomes, a nice picture, but it doesn't tell me how to measure things or how to do things.
No, that's exactly the point.
Let me add one question mark to Jerry's question. Are you talking about a specific line of the transmission circuit, or are you talking about the whole brain average? I mean, your signals, and when you do a Fourier transmission Fourier transfer, right?
Right.
You convert between you're talking about a certain circuit and what's going on, the wave in that circuit. And so you map it into a different domain. Now, what you are showing us here is that a specific circuit of some kind, like X amount of neurons formed a chain of, let's say, like a Christmas lights in your building. So that's one thing. But another situation, especially when you go back to McCullough and Pitts, when what we call a concept emerged, an aha moment, and it's kind of like the whole brain thing, right?
Yeah.
I'm not very clear about this, so maybe you can give more explanations.
Okay. So what
Follow
I
up
was,
to Jerry's
yeah,
question.
no,
Don't forget Jerry's question.
okay, no, to go back to Jerry's question, a neuron theoretically, okay, it's an isolated entity, okay, but it has dendrites and it has axons, and the dendrites and go couple with the axons, and you get the synapses. I mean, even though they're not physically fused, there is a synaptic cleft there, but they're close enough for communication, right? So each neuron inside it, it operates like a closed system, doing certain things inside metabolic activities and communication activities, but it is completely open to the whole brain through its 1,000 synapses, and it is making all kinds of connections, right? So that makes it the whole thing as a network, very large internet. That is what we have. Okay.
Yes, I agree, and that was the point of my pointing this out.
Yeah.
That it is without the capabilities of summing up the inputs.
Yes.
At each of the synapses.
Yes.
Your mathematics becomes well, it's generative biologically, it's generative to give a particular signal from a particular synapse, as you note by the firing and the electrical changes you demonstrate.
Right.
But to move from that level to the next level of the function of the brain or other things, how is the mathematics to work?
Oh, first of all, from single synapse, you get a very a small amount of current. Actually, I have a slide on that too. I wasn't going to show, but it's picoamperes of current flow through those dendrites, and we are getting microvolts of membrane voltage changes. So from a dendrite, you get one branch is called a spine. One branch is called a dendrite, and in each dendrite you have lots of little spines, and each spine is connected to the axon from the axonal boson. So what you have is lots of wires coming into one large wire, and the beautiful thing about it is when there is a coherence, collective firing of many of these bosons coming into these spines, then the summed voltage becomes a fairly significant amount, and that's what is the spiking, and that propagates through the main dendrite into the nucleus.
Thank you.
That is the spiking process.
Yeah.
Right.
Thank you.
So the whole mailing list of this this neuron received the same strength of the signal, right?
Not the whole neuron, only one branch. It has 1,000 branches. One branch receives coherent input, and that can fire. Okay, so that is why it becomes like a huge n by m mapping. You have n number of dendrites coming in here, n number of spines or synapses, and you have another m going out. So each neuron is doing an n by m mapping. Humongous. Okay. And
so the
is
output is not together. It's like a mass mailing thing. It's selective.
Yeah, see, brain is the supervisor, and you cannot have a supervisor for the supervisor, which means when these things are happening, when the input is coming, there is nobody to tell that input to say where to go. Okay, so this current starts to go in, and it releases what is called a vesicle, which contains the neurotransmitters that is in the center of the nucleus. And then the vesicle goes to the axon and then goes into the bosons, and there the calcium comes in and releases those neurotransmitters, which jump across the synapse. So the whole thing is electrochemistry. Okay, so it is the neurotransmitters that are really opening and closing the gate. And that is why I was saying in my previous slide, it is the rate of change of conductance. That is when the receptors open, that is when the current can flow in. So go ahead.
That was determined by the neurotransmitters are determined by another circuit, like a pituitary. The all kinds of chemicals.
Right.
So exactly. Including my mood, like say,
yes.
I have a happy mood, or I have a sad mood, and the neurotransmitters does the different things.
Yes.
The whole calculation is different.
I'll send you a paper. In fact, I sent that to Morris, and this is looking at the different. Actually, I sent that paper probably to you all. It's a paper by Lauheim. It's called Neuromodulators, and you can using the acetylcholine, norepinephrine, and serotonin. Norepinephrine, dopamine, and serotonin. If you use the 3, you can get a cube, you can get 8 corners and becomes 8 emotions, and the center is the pace. So you can get 9 emotions coming right out of this neuromodulator release, and that's what triggers. And those are, so whenever there is a stimulus coming in, 2 things happen. One is, let us say the auditory input, the auditory system converted the acoustics into an electrical pulse, and that needs to be propagated. But you need to know whether this input has any salience or relevance to my livelihood. And that's where these neuromodulators come in. And the 2 together determine which path this is going to take. And that's what becomes the short-term memory and eventually long-term memory. So 2 inputs determine. So it's like the signal lights in a highway. So the cars are going, but the signal lights are opening and steering the traffic flow. Jerry?
Oh, I think, your explanation is getting better in terms that you have to add more things that Jason is looking for, and most readers would want, is a more graphic description or diagram of how the summation of 10,000 different inputs become one output. And that's really the problem.
Sure.
And there's feedback relationships on all of the inputs.
Yeah. Right. I think that probably maybe I have a slide. That would, so this one talks only about the input, all these 1,000 dendrites coming in. They're all happening at different intervals. That is what this picture is talking about. Okay. So the input itself is a random type of input. A Poisson process gives you all kinds of frequencies, right? So then let us now talk about the next step here. And I'll skip this. This I've talked to you before, how the golden ratio comes in. Let's just, I think we can skip this. So this is the slide you're talking about. I should have probably shown this picture. So here is the nucleus, and here is the apical dendrite. That's the main dendrite that is going out with lots of branches here. And within one branch, if you look at it, there are a lot of little snubs or nodules. They're called the spines, and each one of them is again connected to other axons, and that section is the synapse. So you can see lots and lots of synapses in one branch, and then one neuron itself having so many branches. So this is the input, and the output goes from here through the axon. And the axon itself again bifurcates just like this. And so you get an N by M mapping. And so one neuron is the internet by itself. Okay. And we have only 100 billion of them. And the 100 trillion connections that we have, that is how big the brain is, right? So you can show this in more like a circuit diagram in this fashion here. This is done by Jeff Hawkins. You know, the guy who did the Palm Pilot, and he has this Numenta company here. This is his group's picture. Okay, and so I'm trying to get back to what Jerry was asking. So how this is connected is, it is connected in this fashion. This is the basic canonical circuit inside the brain, or actually any kind of open system. You can say you have 2 systems But this system has its own modality. This could be an ear, or a mouth, or whatever, eye, or whatever. It is taking some kind of modality input. And this could be the top level that is going to have some knowledge. So you can't go from a analog input into a symbolic representation. In between, you need translators. Okay, so this is at a high level. But if you look at a neuron level, you can't go from this one pyramidal neuron straight into another pyramidal neuron. You need to go through interneurons, because these are the ones that bring in both the neuromodulatory input and also making connections when a certain memory is formed. So this is a memory of me. This is the nerve coming from the eye, and this is what is going to be somewhere in my Wernicke area representing your name, let us say. So these connections are all happening like this, okay? And this is feed forward is a communication going through like this. And then this is the feedback, that is the control coming through like this. So this one, if you look at it like this, it's like almost like an infinite connection. So for communication and control going through. But this is a canonical circuit. That means if you zoom into it, it's a fractal structure. You'll keep on seeing more and more connections like this in many different parts of the brain. So you go from by the time I go from the ear to the Wernicke area, we have gone through many, many layers, and each layer works at a different time interval. So the innermost one, first one, the thalamus, is the one working at the gamma interval, which is of 25 milliseconds. That's the first analog to digital conversion. And then you start chunking them into bigger and bigger pieces. And that is what becomes the bits to bytes to words. And that happens in the prefrontal cortex, along with the amygdala deciding whether this is worthwhile storing or remembering and those kind of things. And from there, it goes towards the Wernicke and the Broca area. That becomes the concept and the motor actions. So this could be Wernicke area, and this could be more the Broca motor area. Like that, everywhere you look at it, it's a 2x2 system. This is the canonical circuit, and this forms the open circuit, open system logic. Okay, this could be an individual, and this could be the government. Okay, or it could be the president, and we go through the government here. Okay, so you can have a your local government sending your local senator sending in information here, and then this person acting through the cabinet secretary coming back to making a rule that impacts your individual. So you can see this kind of logic works at microscopic level to the macro level. And then going back to this frequency discussion, what I wanted to say was, you don't have to have an LRC or a mass damper inner stiffness system. You can actually have a transistor that can produce this kind of periodic outputs. And this is what I described before. Jason knows the circuit quite well, right? So we have a transistor with where the bias junction gets the input, and this bias voltage gets charged when one system is running, and this would release. And when this system is running, this gets charged, and then when this starts to discharge, this closes and this charges. So they can do ping pong. And the good interesting thing is, in between you have two different RC filters. One can be a differentiator, one can be an integrator. Okay, the reason I'm dwelling on this is they both can have different periods. And in the brain, this canonical circuit is represented in this fashion because this node here, pyramidal neuron, is actually a transistor. Okay, and this has this bias junction here, and it has this collector junction here, which is the dendrite, and it has the emitter junction here, which is the axon. So the neuron is a transistor, and two neurons connected like this forms a ping pong circuit like this, and they can have two different frequencies. The reason I'm saying this is, one of them brings the sensory input, and it goes to the next level of brain, and that level of brain now gives a control command to say, do something else. For example, when I'm looking at your picture, now I can't understand the whole picture, I need to go zoom into certain section to be able to see Igor's face here on the screen, right? And that requires a command to my oculomotor muscles that will make me zoom and focus onto the portion of the screen. And that is the motor command that is coming through. So sensory command this way and the motor command coming this way. So you can see this sensation and motor action then becomes a resonance. That's what I'm calling as adaptive resonance. Okay, and when the sensation out of this N sensory input connected to the M motor output, when you get that N by M mapping, that becomes our memory. Okay, and also for each sensation, there is a certain action that becomes the attractor. Now, when you store this, going from sensation to motor, you get the storage. And then when we want to act, all we have to do is recall the motor, because every time one step is taken, it'll need your sensation that will drive the motor back, and then it keeps on going. That's what I had presented in the past. Okay, so what I've been talking about, going back to the original conversation, I'm trying to say this kind of control and communication happening in a reciprocal fashion, which we are calling as cybernetics. When this architecture got into the organism, that leads to self-organization. And that self-organization is what I'm calling as adaptive resonance. I mean, not just me. I mean, the Grossberg started it 50 years ago. Okay. So let's just move on.
I'm just sorry to say that I have to
Leave.
take part.
Yeah. Okay. Actually, I'm done here. My presentation is finished. So to summarize it, what I'm saying is, you don't need frequencies. Okay, it doesn't have to be periodic, and it doesn't have to be sine waves. You can have all kinds of intervals, and you can have all kinds of wave shapes. And in nature, typically what you find is a Gaussian waveform, and those are very sharp. And when you combine several of them, what you get is a wavelet. So the wavelet is the typical input to any kind of system dynamics. So let's not be restrict ourselves to this concept of resonance happening because the system has a natural frequency and you are hitting me with the same frequency. No. Okay, that's the bottom line. Thank you.
Great. I don't think we have time to do my presentation, so
I'm sorry.
Another time. That's okay.
Can I just
think,
put one
Ram
worm,
and
one
Mr.
thinking worm in that?
Oh, sorry.
Can I just put one worm in that before I have to go? I'm really sorry, but you know, we have this it is a very elaborate system, right?
Yes.
And one type of resonance is basically the operational one. The next one, the next level is basically the system which develops this kind of systems.
Yeah.
Right. And there we have the next basically learning pattern of, you know, if we call it evolution, that's nice. That's the pattern we recognize.
Right.
But I'm wondering, is it only mere evolution, or is there something which kind of, you know, expedites the process of evolution? So basically, if there is a reason, if there is something more than just clean coincidence that this kind of complex systems emerge. I don't know.
Designer, some
So basically, that's the worm I tried to put in the room.
Right. I know.
And now I leave.
You can believe that there is an intelligent design, or you can believe, if you're a belief system, you can believe there is God and everything happens because of God.
Yeah, no, I'm wondering. I don't believe.
Or if you're an atheist, you can say everything is random and the things, hey, it happens. Right?
Okay, let's just add.
So
just add a neurological connection on that. Neurologically, what's happening is a combination of bottom-up feature detection and top-down pattern imposition, and those two
object recognition.
The couple, they're in resonance, right?
Yes.
Yeah. Yes. That's exactly what I want to say. I'm sorry, I missed that point. The resonance is between the bottom-up communication, which is the feature detection, and the top-down control, which is the object consolidation.
And
I
that freaks
already
me out.
I had a term for you guys. Feed up, feed down. Okay. In classic cybernetics, you have feedback and feed forward. And the feedback forward, you already had a lot of things going on. Now, then you have a feed up and the feed down. That's between multi-layers of emergencies. And moreover, you have a feed left and the feed right.
And that is only because we live in three-dimensional space.
Because you are in three-dimensional world. Exactly. That's what I want to say. They call it bottom up, top down, or feed forward, feedback. Okay.
You just feed up and feed down is within one system. But feed left and versus feed right are between different cognitive systems.
Right. Yes.
You have to feed left to make things simpler, so that the other cognitive system with less capacity can grab it.
Bye-bye.
Okay. And you have to feed right to make it more sophisticated, but less and less people can understand.
You have to feed face.
It applies to organizational dynamics.
Okay,
organization,
so let's see each other next time.
Host isn't allowing multiple presenters sharing for the meeting.